All right, in this video, we're going to talk about computing probability with two outcomes. Another name for this, you might hear this referred to as binomial probability. And I'll actually use that phrase a little later on in the section. And of course, when you see two outcomes, a prefix bi meaning two, that's kind of what we're getting at, is when we have two possible outcomes and we repeat the trial multiple times. That's kind of what we're seeing in this situation. So we're going to look at examples like, oh, you can either win the game or lose the game. What's the probability that you win 3 out of 5 games? So that kind of situation we're looking at is what we're looking at. So let's look at an example right now. The probability of a team winning a game is 3 out of 4, or 3/4. What is the probability of winning 5 consecutive games? So we're going to build up to a really useful, powerful formula here, but start with some basics. Well, the probability that they win 5 consecutive games would be, well, they'd have to win the first game, and then they'd have to win the second game. The probability of winning the first game is 3/4. The probability of winning the second game is 3/4. So each game is independent of the next. So we can just multiply the probability of each individual game, and we'd see, all right, 3/4 times 3/4 times 3/4 and so forth. Really, that's saying 3/4 raised to the 5th power. And we would get 243 over 1024. That's the probability that they would win 5 consecutive games, right? What's the probability that they would lose 5 consecutive games? Well, there's a 1/4 chance that they would lose the game. Either they win it or they lose it. We're not playing soccer here, so they win or they lose. And so there's a 1/4 chance that they lose, and they'd have to lose each of the 5 games. So the same logic would apply, and we would get the probability that they lose 5 straight games is 1 in 1024. So those are relatively simple cases. We just raise the probability to the power that is the number of games they play, right? And we could do the same thing to figure out what's the probability that they win 15 straight games. We'd raise 3/4 to the 15th power and so on. But what's a little more challenging is to think about what is the probability that they win some games and lose others. So if they do the same thing for the whole series, then it's relatively easy to compute. What if they do a mix of things? Well, they could win 4 out of 5 games, and that would look like any of these 5 possibilities. They could win the first 4 and then lose the 5th game, right? And the probability of that would be 3/4 times 3/4 times 3/4 times 3/4. For their first 4 games, they won all of them, times 1/4 for their last game, which would give us a total of 81 over 1024. If we think about, well, what if instead they won the first 3 games, and we're still trying to win 4 games, but what if they win, then they lose the 4th game and win the last game? Well, that would look like this. It'd be 3/4 times 3/4 times 3/4 times 1/4 for their 4th game they lost, and then times 3/4 because they win the last game. That also, though, would come out to be 1024. And what we'll see here is, because multiplication is commutative, maybe we move their loss to the 3rd game, but even if we do that, we end up getting the same value again. And so we see it doesn't really matter where that 4th game is or where that loss is. They're going to have the same probability regardless of where that loss falls. But there are 5 different places where that loss could fall. So in each case, there's a 81 out of 1024 probability that they'll lose that particular sequence. They'll lose that particular game out of 5. So there's an 81 out of 1024 chance that they lose the 4th game. There's also there's an 81 out of 1024 chance that they lose the 5th game. The same probability that they lose the 3rd game. But these are all distinct scenarios, okay? And so really, the probability that they lose 1 out of the 5 games is the sum of all of these probabilities. But let's notice something about these products here. In all of these cases, you had 4 factors of 3/4, and then you multiplied 1 factor of 1/4 in each case. So you took the probability of winning and raised it to the power that is the number of wins you're hoping to achieve. and multiplied it by the probability of losing raised to the power that is the number of losses you were expecting. Okay, but when we look at it, there are 5 different ways for that one loss to occur. So the number of ways they can win 4 out of 5 games is a combination of 4 out of 5 objects, right? So they have 5 games to play, and they're choosing 4 of them to win. And so this would be the number of ways that we could choose 4 games to win. But that has to get multiplied by the probability of each particular scenario where they lose. So there's one scenario where they lose 1 game. This is a different scenario. This is a different, and there's 5 different places where that loss can fall. So we have 5 times 81 over 1024, and we get the probability of 405 divided by 1024. This is the probability that they'll win any 4 of the next 5 games. That's this probability right here. But let's notice the patterns here, right? They played 5 games and we chose 4 of them to win. This is the probability of winning any particular 4 out of 5. It's always 3/4 the probability of winning raised to the 4th power times 1/4 the probability of losing raised to the 1st power. So if we want to win 3 out of 5 games, it'd be the same idea. We would do 5 games. We're choosing 3 of them to lose. In each of those different scenarios, they have to win 3 times and lose 1 time. 2 times. 2 times. They're going to win 3 and lose 2. And if we type that into the calculator, you'll get 270 over 1024. So there's a 270 over 1024 chance that they would win 3 out of the next 5 games. And we can keep working through all these possibilities. Maybe they win 2 of the next 5 games, so change this one to a loss. Well, they have 5 games. We're choosing 2 of them to win. So this is the number of different ways that those wins and losses could fall. But the probability of winning, they're going to do it twice. And then the probability of losing, they're going to lose 3 times. So we type that all in the calculator, we get 90 over 1024. Maybe we only want to consider what if they're going to only only win 1 game. So again, change these W's to L's. Well, again, we have 5 games, and we're choosing 1, only going to win 1. And we want to multiply it by the probability of winning, but they're only going to do that once. And the probability of losing, which they're going to do 4 times, and that comes out to be 15 over 1024. Okay. And so the last case would be that they lose all 5 games. We already computed that as 1 out of 1024. That's the probability, essentially the probability of winning 0 games, same logic. And just as an aside, you'll notice if they play 5 games, they have to win either 0, 1, 2, 3, 4, or 5 games. If we take the probability of winning 5 games and add the probability of winning 4 games and add the probability of winning 3 games and so forth, we know that these would have to add up to 1. They have to do one of these things. So if we took all of these probabilities plus this one and plus this one that we had up here at the top that we started with, all of those probabilities would have to add to 1. And they do. If you take the time and add them up, but I don't want to waste your time. They do add up to 1 because they have to do one of those 6 things. Okay. And so this is an example of a Bernoulli experiment or a binomial experiment. And what we can do is generalize what we're seeing up here into a very powerful formula here. And that formula is constructed as we see right here, where n is the number of trials. In the one case there we did the number of games. R is the number of successes, that was winning a game. How many wins were they going to get? And then we want to multiply by the probability of success, the probability of winning, raised to the number of wins, number of successes, times the probability of failure, losing, times the number of losses, which would always be the difference between the number of games played and the number of wins, or the total number of trials minus the number of successes, n minus r. So this is our formula for a binomial setting. Okay, and in the next couple of videos we'll practice using it to actually compute the probability, so we don't have to go through all these long-winded calculations that we just did. So we can be expediting this process quite a bit by using this formula, and actually we'll see we can use the calculator to do it even faster. So that'll be in the next couple videos.